Thank you very much. I love seeing people in the front row. That's a rarity for me. Everyone's really scared, but I don't bite much. Okay, so PyData London. So thank you for coming to my talk. So today we're going to give a little intro to the streaming landscape. And then I'm going to talk a bit about stream processing and the benefits of online machine learning before introducing River, which is an open source real-time machine learning Python library. I think most of you heard the last few minutes. So my intro is Tin Shui. I'm the VP of Data, and I look after developer relations at Qwix. So Qwix is a stream processing company focused on Python developers. My background is in data engineering, so I was also a head of data. So I helped companies determine their data strategy and implement it, and where relevant, use stream processing and think about real-time data as a first-class citizen. Naturally, I'm into real-time data and the AI ecosystem. It's been absolutely exploding in the last few months and in the last year or so. Keeping an eye on that. It seems like there's a new startup or a new library launching every week. So I like to keep an eye on that. I believe in the mantra less is more. So I'm a big fan of simplicity. I think as humans, we tend to think that success lies in complexity. So we are just busy making things complicated for ourselves. But I'm usually the person in the room that says, can this be simpler, please? And I believe in getting started sooner. There's so many libraries. I love being at PyData because there are so many different libraries and so many different projects going on at the same time. Such an inspiration to be around all the maintainers and the contributors to these libraries. So get started. It's just a pip install away. Also, that's my LinkedIn up there, so if you like everything you just heard, then please add me. Okay, let's talk a bit about how data is collected in a real-time scenario. So everyone probably knows what a database is. Hands up if you don't know what a database is. Okay, yeah, that always gets a laugh. You probably have several databases on your phones actually running, and they're everywhere, right? And what you do with these databases is you access the data by looking them up in tables. Now, with stream processing and real-time data, you don't use a database. You use something called a message broker. And a message broker, the parlance is you produce two topics in a message broker, and you consume from them to read them out. The CEO of Qwix, like my company, he always describes it pictorially as a message broker is a database that is fallen on its side, which I always thought it's great, but it's kind of stretched out as well. This is a bit about the landscape of streaming brokers. Kafka is the most predominant one. Can I have a quick show of hands for anyone that has developed with any of those technologies on the screen? Oh, wow, this is quite a lot. There's probably 20, 30 people. Keep your hands up if you've deployed to production. Okay, about half of that. So that's pretty impressive. So I think I'm in the right room for this. So to give everyone else a bit of a background on what's happening here. You've got Kafka, which came out over a decade ago. It was created at LinkedIn, and it became an Apache project. And we have Pulsar, which is also an Apache project, which came out just under a decade ago. Now, these technologies came out of companies that were larger, like LinkedIn. And so we're talking about enterprise companies, so large companies that work with huge data at great volumes and great throughput. And for them, they all develop in Java. So naturally, the landscape for real-time data and streaming data technology emerged and was matured in the Java landscape. And what we've had in the last few years is these startups have come along to kind of disrupt that a little bit. The new wave of data engineers that I keep meeting are those that don't come from a classical stack like I did, which is very much based in Java and JVM, like Java Virtual Machine languages, like Scala and Clojure. They come from different languages. So Red Panda there on the bottom left, Red Panda on the bottom left there is a completely Kafka API compatible broker, and it was written in C++. And you have WarpStream on the top right, which is written in Golang. So what you're seeing now is this new wave of startups that are trying to provide a good alternative. And one of those great alternatives enables you to start working with Python. I think I'm in a room with a lot of Python developers. Hands up if you know Java or develop in Java day to day. All right, there's a good 10, 15 of you. So there's still some coverage there. I think some of those hands were the same Kafka developers that put hands up, right? The thing that's always been difficult is to start using that real-time data in Kafka in a Python setting. And to explain a bit more about that, I'm going to go a bit into the background of Quix, the company I'm working at. And it comes from an F1 racing background. So those are the 4 co-founders there. They worked at McLaren Formula One race. It's a Formula One race team. And I should localize this for the American visitors. It's like NASCAR. And this was a naturally very time-critical environment. Like racing teams are extremely competitive. They need to get that data moving. They got to get that data out, get the insights out, and this will enable them to tune their cars, tell the driver when to come in for a pit stop, things like that. So extremely time-critical. They started off with databases too. So they started using it when the throughput got really high. They realized the databases couldn't keep up, so they needed to look for a new solution. So with high throughput data at high volumes, all roads naturally lead to Kafka. So that's where they found themselves. So yeah, this is kind of representative of the environments at one extreme where you really need to deal with very much data. So there's like in excess of 300 onboard sensors. There's 2 cars going around the track. You do the math, it's a lot of data. You'll notice I'm not in the picture. This was 4 years ago. I arrived and landed about a year and a half ago. I am trying to carry on with the whole racing heritage. The joke internally is that I was hired for my driving skills, not my data skills, but the jury's still out on that one. So we got together and we created this open source library that was based in Python called QuickStreams. And QuickStream started off not as a 100% pure Python library. It had some C# in there. And what we found was like real-time data and working with data in Kafka hasn't reached the mainstream yet in Python land. So we wanted to make that as seamless and as simple as possible. So we chose to go 100% Python, which means it's completely Pythonic, which means you're not wrapping Python around other languages like Java. So when you're developing applications, you don't develop and deploy to production in day one, at least I hope not. You kind of iterate your way. You make mistakes, you debug your code. And the benefits of having 100% Python is you can do line-by-line debugging. So it really helps get you there. We've embraced the concept of data frames. We call them streaming data frames. So you see here that we've defined an input and an output topic. And from there, you load it into a data frame. So every time new data arrives in a topic, it appears as a data frame. And you're able to use columnar like notation to manipulate that data. And this is also important for stream processing when you're implementing machine learning because you need to hold state. So we have stateful operations. So we have window functions, which you may be familiar with. And you can also have access to a high-level state object, which helps you manage state. So in this case, it will be a machine learning model that's working in real time. And Python developers don't always like to play around with managing their own Kafka and Kubernetes and Docker and CI/CD, so we have a managed platform for that. So that was the background on kind of like the streaming landscape and stream processing. But stream processing is really required in machine learning. It's what makes online machine learning possible. It's like the flux capacitor. So what is offline or batch machine learning? So I've broken it down into 2. So there's the concept of offline inference and offline learning. So I'll go through each of those in turn. So for offline inference, the predictions are generated from batched observations, and you generate many predictions at the same time. And these predictions aren't available for real-time purposes. So an example would be, I've worked for a large publisher before on a recommender system, and we used Spark to process clickstream data. So users that were clicking around their website, we would get all that clickstream data and we'd pre-generate recommendations for everyone. There was like millions of users. So you generate like up to like 10 recommendations for every single user, and then you store that in a database somewhere. And at some point, there's another team that will run a scheduler that would kick in and it would read from that database and then pull out the recommendations and email everybody. So that's an example of offline inference. Offline learning, this is the most common type of machine learning. It's the de facto one, so whenever you hear machine learning, this is the type of learning that's happening. It's about fitting a model over static data, also known as historical or bounded data. And what it is batches of observations are processed in one go. And for offline learning, what you're doing is you're fitting a model over static data. You're dealing with batches of observations at a time, and it requires a lot of memory. Most of the time, that data doesn't fit into memory, so what you need to do is you need to chunk it. So you would partition it out into smaller chunks, and then you would have parallel workers working at the same time, and then you do your joins at the end to get your aggregations. And offline learning it became the de facto, and it's incredibly popular because it's really easy to reason about. Like humans don't deal very well with 4 dimensions. Like when you think about time, we don't always do so well with it. So we created these constructs. So when you deal with data sets, you'll see them described as, oh, they were between the years 2011 and 2012, things like that. So bounded data is just very easy to reason about. So you can think of data in terms of days, weeks, months, years, etc. So it makes sense that static data would be used in this way. You've got a lot of well-established processes and tooling for machine learning offline, and it fits. I made this number up, but it feels like about 99% of use cases. So you could use it to solve almost any machine learning problem. So data science and batch processing are deeply intertwined. So let's go on to online or streaming machine learning. Before we do that, let's think conceptually about how data travels through systems. Like what's the journey of data? So the first thing generally is that it's generated, and data is always generated in real time. So an example would be a user clicking around on a website. So that would form the basis and be collected as clickstream data. And then you've got another example, like a measurement taken by a sensor, periodically. So that's another data point. So this data is generated in real time. And what happens is it typically stays in motion. So it will move into something like a message broker, and then it gets pushed immediately into an at-rest state. So it will take that same data and it will write it to a database or object store for the most part. And then at some point, a scheduler will kick in and it will read that data and it will process that data in batches. So the question's always been, why don't we deal with that data when it's in motion? Like when it's still in the message broker, why don't we do anything with it? We always wait some time later to deal with it. And the pushback's always been that it's been complex and difficult. Yes, from that Java landscape that I described, it would have been difficult. You've got this impedance gap between thinking about different languages, debugging in different languages, trying to work with Python at the same time. So it used to be difficult, but times are changing. We've got these startups that are trying to change that. And you've got a lot of companies that are managing Kafka and providing lots of fully managed services. So it becomes less and less difficult. So onto online machine learning. So I'll break it down in the same way into online inference and online learning. So online inference, it's real-time predictions. It's when you use the model to make predictions on demand, and you're fetching necessary features at the time of request. So when you're doing computation, you keep everything light, you keep your features in a feature store. For example, like Hopsworks, whose booth you may see outside. So we use Hopsworks as well. You've got online learning, which is real-time training. So this is fitting a model over streaming or as also known as unbounded data. And the main takeaway here is that you're learning one observation or data point at a time. And with online inference, this is what most people mean when they say they do real-time machine learning. When I ask, I talk about machine learning and real-time machine learning a lot, and I say, do you do that in-house? They always say yes, but this is actually what they mean. They're not doing any learning, it's the actual inference. It's very straightforward to do. There's really good tooling for that available now, like whole platforms deal with it actually. And then this works really well with batch models. So everything that you created with offline learning, you can reuse for online inference. And it has a really mature tooling ecosystem. So for things like selecting the right model and serving it, they all exist. And this is kind of what online learning is. So you've got observations that come in, and occasionally with these observations, you get a ground truth. So you're able to learn on that data point, or you get an event through that's requesting a prediction, or you generate that prediction from that model at that moment in time. So you're doing one or the other. You're fitting a model over streaming data. That's the main point. And you're learning incrementally with one observation at a time. And most people don't do this. Like I look around the room, everyone's like, no one's putting their hand up saying, oh, I do this already. Like no one really does this. It's a pretty radical approach. And the reason is not all algorithms or models are suitable. That's some of the first things you'll go across, and you'll realize we can't use everything from the batch world in the online world. It naturally works well with unsupervised methods, things that don't necessarily have a label available at the time. But supervised methods also can work and require some thought, because the ground truth or the labels may arrive at some point in time. So you need to create that system that will collect them and enable you to map it to the original prediction and then present it as a learning point. And since that data is streamed in, there are many unknowns. So you kind of In the online machine learning world, you just accept everything that you're given. So features may disappear, reappear later between like different observations. You never really have an understanding of the classes and the cardinality. Like you don't really know what's going to happen. Data arrives, there's features that are there that used to not be there, you just accept it. But there are lots of benefits to using online machine learning. For one, historical data isn't needed. I was talking to somebody here about Raspberry Pis and having environmental sensoring like in your home. Like I have some kit, and the first thing when you're dealing with like any sort of exercise or project with machine learning is you've got to find the right data sets, right? That's why, partly why Kaggle is really important as a resource. Like it's got so many data sets available. With online machine learning, you don't need that historical data. The weights are kind of like start from 0 or evenly balanced, and it just learns with data points as you go in. This is great for if you're starting a Raspberry Pi kind of environmental sensing project in your home, for example. Like you don't have historical data, so you can get going from day one. And this would be true for a lot of other companies too. They could suddenly start using data without having a backlog of data. It working with one observation at a time means it requires less CPU and memory as well. So when I show you kind of like the examples of the data coming in, you'll see why. But generally, a single data point is not much data. And it adapts to new data and trends because models are updated as soon as new data becomes available. As soon as that ground truth comes in, the model is updated. So it's really great for dynamic environments where like data distribution changes all the time. It doesn't require retraining. It's just continuously retraining. You contrast that with batch, where once the data has been fit to a model, it needs to be retrained from scratch. So the process is usually to collect historical data, you clean it, you transform it, and you create your predictive models. And in the time that it takes to complete that, new generated data may have arrived, which you append to the old data, and then you use that, and it all adds up, and then use that to retrain new models. So everything goes up. And it being continually learning, it's resilient to model or concept drift. So concept drift is when the underlying distribution in the data changes over time. So the relationship between the features and the target like go out of whack. So what that results in is a degradation in prediction and predictive ability. So online machine learning is really sensitive to that and can adapt really well. The pandemic would have created a concept drift, for example. Suddenly our shopping habits were suddenly very different. We were buying a lot of toilet paper. We're buying a lot of other things we probably wouldn't be buying in bulk. So some of the smarter machine learning systems would have adapted to that. And there's also the TikTok paper as well, which you can go read from ByteDance, like how it's able to detect within a few swipes your exact preferences. So yeah, check out TikTok if you haven't already. So on balance, the model is a stateful, it's an ever-changing object. And here are the use cases. There's really so many. Like when you think about real-time data, anything that benefits from low latency predictions and works with current context, like new data that's arrived, that could potentially be a use case. It's really table stakes for certain industries like banking, where you have fraud detection. So you may have received an alert or an SMS like on your phone when, like on a random day perhaps, that someone had cloned your card and like there was a transaction going through in some other part, in some other continent somewhere. Like I always get those, and that would only be possible with real-time machine learning. You probably use recommender systems and as well as personalization from a lot of these like popular online services like Netflix and Amazon. And one thing that I'm seeing emerging is in medical devices and in the wearable space. So this has implications for healthcare. So things like for elderly, if they have a wearable and you're able to detect falls, that's really a benefit, as well as for things like continuous glucose monitoring, etc. Like getting all that data into one place and being able to analyze it like in real time is really important. So we're seeing a lot of emerging things even in these existing fields. So with batch and stream, often I see it as batch versus stream, offline versus online. So I made this meme. So yeah, you always have to choose, but the real answer is this: you actually use both. So don't sweat it. Try to use both where appropriate, and use batch and stream together because they are complementary. Like one does not replace the other. use the stream data for current context and use the batch for the historical. And historical data just generally, with the maturity of our models and our evaluation systems, they tend to have better accuracy anyway. So I always recommend you use both. Most teams will try to fit streaming into a batch system, but I find it's much easier to fit batch into a streaming system because I hold the opinion that batch is a specialized subset of streaming, because essentially you're taking the same data and you're kind of slowing it down. With streams, events are the foundational unit, and you're able to rewind and play everything back in order to recreate any historical state from previous. So this is kind of what it might look like if you try to add streaming to a batch system. You've got a double distributed system approach where you have a separate real-time layer and a separate batch layer that's trying to service queries, some of which need to return predictions. And these are the reasons why you're maintaining two different code bases, two different sets of algorithms and models. So you're kind of doubling up your effort. You've got to make sure they stay in sync. Where do you read from when there are delays? Double the infrastructure, double the fun, double the money, double the team. It's something you want to avoid. And you can do that by adopting something called a Kappa architecture, which is event-based. This was coined by Jay Krebs, who one of the creators for Apache Kafka back in 2021. And his view on it was everything goes through the streaming layer first. It hits that layer first. And the batch layer, the storage, so you see a little database there, that's essentially what you write to after you've processed it as a stream. So you have a single core technology stack with a single entry point. You have real time, and it's possible to recreate historical state. And you've got improved data quality because you have guaranteed ordering because they're event-based. And the other benefit is that if you need to scale out, it's very easy to do that. It's quite trivial to do that because Kafka has the ability to scale out much more easily than scaling out a database using replicas, etc., and sharding. So batch and stream together solves all use cases. You've got offline, which solves most machine learning problems, and you've got online, which solves problems where the current context is important, and you probably need both. So here are a couple of projects that aim to try to solve that. So you had Cream, which was a project that started with the mission of providing pure online machine learning models. And then there was Scikit Multiflow, which was a project specialized in online machine learning models, but also with a bit of a focus on small batches. And there was a lot of crossover in the mission. So the project leads got together and determined that the focus should solely be on online models. And they merged and River was born, so to speak. And I'll give you the summary of River and what it's all about. It was heavily inspired by scikit-learn, so they were really focused on developer experience. They wanted to encapsulate a lot of the knowledge you already gained from scikit-learn. Like most people, most data scientists who learn on their learning path, they will learn via scikit-learn. It's the fundamentals, and it's something everyone can grasp. So they relied on that knowledge already being there and are building on top of it. It's great for general purpose ML tasks. So you've got regression, you've got classification, unsupervised learning, etc. And it can be used for ad hoc tasks as well. So things like computing online metrics and rolling window metrics. So you can do a lot of different things, quite flexible. It comes preloaded with a lot of different models. So you've got use cases that you can solve, such as anomaly detection. You've got time series forecasting. With anomaly detection, you've got things like Gaussian scorers, you've got half-space trees, and with time series forecasting, you've got statistical models like Holt-Winters. So it's really quite comprehensive. They also come with some data sets as well. I can show you some examples in a moment. So you've got, I think, like Iris, and there's a lot of the famous ones you may have used already in Kaggle that are already available as well. So you can just import that in a package and get going straight away. You've got models that cope well with concept drift. So I mentioned that before. There's a drift package inside the library that you can use. It's got support for adaptive windowing or ADWIN and the Page-Hinckley method. And the last real concept that kind of blew my mind a little bit is that everything is a dictionary. So the choice is made not to use any other kind of new types, but to use the Python primitives. So everything's a dictionary. Here's an example of a data set that you're pulling in. So there's a dictionary there. And in this case, we're just importing in the ride durations for New York taxis, and we're running it in a loop. So we're iterating over it. The thing with And here's another example. And everything being a dictionary makes the features really explainable, because in offline machine learning, you're often using numerical representations. So you're using NumPy arrays, and with NumPy arrays, them being arrays, you need to ensure that the ordering is correct, because each position in the index corresponds to a specific feature. And it's designed this way because you benefit from matrix multiplication and vectorization. But with online machine learning, because you're dealing with observations one at a time, it's not possible to benefit from vectorization. Like, vectorization is based on essentially batching things up. So the decision was made to go with dictionaries, which makes them human readable, which are great. They're extremely explicit. I think as data points come in, you can see features appear and disappear. There's no deserialization or serialization into different types, so super clear. So everything's a dictionary, including the models. So in the bottom right there, that's an example of a model. You'll see the features with their associated weights next to them. And I mentioned before that an online model is a stateful object. And since they're dictionaries, every time you have a new observation with a new feature come in, you literally add it as another weight. And generally it will start off with 0, and over time as more observations come in and the machine learning model learns, it will adjust the weights. The other main benefit of it being a dictionary is that you can take a trained model and easily, you could pick a lit, or you could just dump it to JSON and you can save it. You can back it up to disk or cloud storage, which facilitates really simple snapshotting and recovery. So you could have an evaluation model run, you could evaluate that model, and if you see a degradation in its performance, you can roll back, and like it's as simple as loading a new dictionary in. And this is kind of like the way it works. You've got the concept of predict one. So you can make a prediction, or if you have access to the label, you can learn once on that single data point. So as you can see, it's reminiscent of scikit-learn. Normally, you need to compute your own metrics as well. So here's an example of how you would do that. You would keep an eye on the actual predictions and store them. And you would also store the actuals that you get later, the ground truth. But with River, you have metrics packages, so you don't actually have to do that. So in this example here, I'm using a logistic regression model with an accuracy metric. And accuracy is a very simple percentage expressed of how many items you got right. There's a lot of different other metrics that you could pull in. The popular ones are represented like precision recall, F1 score, etc. So there's way more than that available. So you've got those out of the box. And another important thing you'll need is scalars and this concept of a composable pipeline. So there you'll see that I've created a pipeline that uses a logistic regression model. And in the first stage of that pipeline, you're using a scalar. So you can use different types of scalars, which will kind of like normalize your data. So if you want to use the most simplest one, it'd be something like a min-max scalar, which scales your values to a fixed range between 0 and 1. So having that is really important, because it enables your data to become normalized, and that will result in better accuracy. And to evaluate the model performance, use progressive validation, where the target is revealed to the model after it's been made its prediction. So this is how you could test the model offline. If you did it in an online setting, you can introduce a delay, which would then progressively evaluate it over time, because you're slowly kind of like drip feeding in the ground truth. So this kind of validation works really well because it's representative of real life use cases, like with click streams, like you're waiting for an affirmative click, that a conversion, like a click through has been made, and if it has, you would register that as the ground truth as being a good prediction. So this helps you to build that out. It's got this concept of print every, which I really like, so you're able to print out the accuracy over time, so you can kind of keep an eye on it in a very simple way. I'm going to finish off just with, there's really so much to go through with River. It's hard to pick favorites here. I work a lot with anomaly detection, so that's the part of River I spend a lot of my time, but there are lots of different recipes that will get you started here. So I went through a few things here, but you've got hyperparameter tuning, active learning, multi-arm bandits. There are recipes ready to go, so you can check the documentation to get started today. And the API is really, really excellent. There's a lot really covered there. So I mentioned anomaly detection before, so you've got Gaussian scorers and half-space trees are becoming really important. Half-space trees they're a type of isolation forest where the anomalies happen in like quite far apart, so they're ideal for anomaly detection. So I love using that one. And you've got others around time series as well, like forecasting metrics. So there's quite a lot going on there. So yeah, that was River. It's a package that works really well, I find. It's quite radical, and it kind of still blows my mind that more people don't use it because it's so simple. To get started with River, you can install the package and start running things in loops just to test it out locally. But to start building and thinking about production, you're going to need other components. So one being a message broker like Kafka, and you'll also need a stream processor. I'm unbiased. I think you should use QuickStreams. I think it's probably the best stream processor out there for Python developers. So check us out on GitHub, follow and support us, and find me on Slack. So thank you very much.